In this portion, we're going to take a very close look at the stress strain curve, and we're going to understand what different regions of this curve tell us about a material. And if you want a bit of a closer look at this, I highly recommend this video by the Efficient Engineer, Understanding Strength, Ductility, Resilience, and Toughness. When we apply a tensile load to a sample, initially the response is going to be linear. As more force is applied and as the amount of stress grows, the amount of strain that we see is going to be proportional. So we see this linear region at the beginning of the curve. We call this the elastic range, because in this range, the material will behave elastically. That means if the force is removed, the strain will recover and the material will stretch back to its original size without damage. As more force is applied, the relationship will continue this way in a linear fashion. This continues until we reach the point known as the proportional limit, where this elastic relationship between stress and strain ends and we start to see what is known as plastic deformation. So this is the first region of the curve worth examining. Within the elastic region, we can determine the material's modulus of elasticity. This is a really key property about a material. It tells us how much it will deform under different types of loads. The modulus of elasticity is equal to the stress divided by the strain at any given point along this line. Without even considering any numbers, if we're looking at two different sets of sample data that are plotted on the same axes, we can tell a little bit that helps us compare the two materials just by looking at them. If this line is steeper, that indicates a material that is going to deform less under a force. In other words, a stiffer material. And if the line slopes more as stress is applied, then we're looking at a material that is more elastic and able to stretch more as force is applied. So which of these materials has the greater stiffness? Again, this elastic behavior is important. Within the elastic range, if the load is removed, the test sample will return to its original length. This is how engineers want materials to behave. They're going to stretch as forces are applied, but we want to make sure when the force is removed that the piece of material is going to go back to its original length, and we're not going to run into any issues with parts lengthening or stretching out of tolerance. Again, at the top of this line where the proportional relationship ends, that's known as our elastic limit. Beyond this point, any stress that's applied is going to start to have a larger and permanent effect on the length of the sample. This region of the curve also helps us understand a concept called resilience. Resilience is the amount of energy per unit volume that a material can absorb while in the elastic range. In other words, this is how much energy a piece of material can absorb before it deforms permanently. And resilience is defined by the area beneath the stress-strain curve, specifically in the elastic region. So if we find the area of this triangle, we have a number we can use to quantify and compare the resilience of two different materials. This is a function of the material's yield strength as well as its elasticity. So a material that has equal strength but greater elasticity is going to have a triangle here with a larger area. Materials that are stronger and more elastic are going to be more resilient. So the top of the elastic limit is a point of a lot of interest to us. It's called the yield point. The yield point, where the elastic limit exists, is where we start to see very small increases in stress producing a much greater strain. And this deformation after this point is permanent. So even if the force is removed, the elastic portion of the strain will recover, but any portion of strain past the yield point won't. This is the point at which an engineer considers a piece of material to have failed. It's important to note, though, that this doesn't necessarily mean that we've fractured. It doesn't mean that the piece of material broke in two. It just means that we have stretched it beyond the point where it's going to go back to the way that it was. So in engineering terms, this is what we call failure. This brings us to the plastic portion of the curve. All of the deformation that takes place beyond the yield point is called plastic deformation. This is unrecoverable permanent elongation, where even if the force is removed, we're not going to see the sample returning to its original length. Only the elastic portion of the strain will bounce back. Again, plastic deformation represents material failure, not exactly fracture until we reach the end of the curve. But when the parts were designed for their given application, they were designed with very specific lengths and dimensions. And at this point, even if the force is removed, those parts are now outside of their allowable tolerances. They're longer than they should be in order to operate properly. What's interesting to note here on the curve is that as we get into plastic deformation, our test sample is continuing to elongate, and our cross-sectional area is starting to decrease. The sample is getting narrower where the breakage is going to occur, but at the same time, its ability to carry the load is still increasing through this range. So how is that possible? How is the material getting stronger while it's getting narrower? The simplest explanation here is that the weakest point keeps being stretched and keeps becoming stronger. This stretching and strengthening keeps occurring until the decrease in area overcomes the increase in strength. The point at the top of the curve is what is called the ultimate tensile strength. This is where the ability of the material to carry a load reaches its peak. After this point, the force required to continue straining the test sample is actually going to decrease. This is observable in the actual tensile test with a phenomenon called necking. This is where the diameter of the sample visibly gets smaller as more and more force is applied until eventually we see fracture. So which of these materials has the greater strength? After we reach the point of ultimate tensile strength, if continued force is applied, necking is going to continue and the cross-sectional area of our shape is going to continue to decrease until fracture occurs. Fracture is where our material actually splits in two. The plastic region of the curve tells us a little bit about the material's ductility. Ductility is the amount of plasticity before fracture. In other words, the greater the ductility, the more a material can be deformed in tension before it actually breaks. For a lot of applications, this is actually very advantageous. We usually don't want our materials to just instantly fracture after reaching their yield point. That would be what we'd call a brittle material. The idea of malleability is very similar to ductility, except that it applies to plastic deformation in compression. Malleability is the amount of plasticity before fracture when something is pressed, squeezed, hammered, etc. Which of these samples was the most ductile? A is the most ductile material, which we can see from the amount of stretching and deformation that went on before fracture. C was the least ductile because we see a really brittle shear where the material split, and B is somewhere in the middle. There's some amount of plastic deformation, but not very much. Brittleness is material failure with little or no ductility. This is a lack of ductility, but not necessarily a lack of strength. Brittle materials can be just as strong as ductile materials. That is, they can reach the same ultimate tensile strength. The difference is how they behave after reaching that point. Which of these graphs represents the more brittle material? The graph on the right shows the more brittle material. The graph on the left shows a more ductile material. In the ductile example, we see a lot of deformation in the plastic region of the curve, where in the brittle example, fracture occurs very shortly after we reach our ultimate strength. A lot of materials are prized for their toughness. Toughness is the work per unit volume required to fracture a material. This is similar to resilience, but resilience was the work per unit volume that a material could withstand before permanent deformation. Toughness also accounts for the energy that a material can absorb even during plastic deformation. Toughness is defined as the total area under the stress strain curve from the test initiation all the way to fracture. So this is a function of strength, elasticity, and ductility. A material that has high strength, high elasticity, and high ductility is going to be able to withstand a lot of work, a lot of energy. It's going to resist fracture even under lots and lots of stress.